close your eyes, or perhaps just soften your gaze and allow your mind to drift away from the immediate world around you. Let the sounds of the day fade into a quiet murmur, and imagine, for a moment, the vast, unbroken canvas of the night sky. When we look up on a clear, dark night, far away from the glowing lights of our cities, we are greeted by a scattered sea of silver dust. These are the stars, the distant suns, the ancient fires that have burned for billions of years in the profound silence of space. To our eyes, the universe appears still. It seems like a frozen tapestry, a quiet painting hung in the gallery of the cosmos. The constellations remain in their familiar patterns, comforting in their predictability. Night after night, year after year, the hunter holds his bow, the bear circles the pole, and the river of the Milky Way pours across the zenith. This stillness, however, is an illusion, a trick played upon us by the sheer, unfathomable scale of the universe. In reality, nothing is still. Everything is in motion. We are on a planet that is spinning gently on its axis, rotating beneath the warmth of our local star. Our sun, in turn, is pulling us along as it drifts through the spiral arms of the Milky Way galaxy. And the Milky Way itself is moving, caught in a grand cosmic dance with our neighboring galaxies, all drifting through the boundless ocean of the universe. What orchestrates this endless, quiet ballet? The answer is gravity. Gravity is the great, invisible architect of the cosmos. It is the most familiar of the fundamental forces of nature, yet it remains one of the most deeply mysterious. It is the gentle pull that keeps our feet planted firmly on the Earth, the unseen tether that holds the moon in its orbit, and the silent sculptor that shapes the fiery birth of stars from clouds of cold, dark dust. For centuries, our understanding of gravity was absolute. It was a universal law, a steady, predictable rule that applied everywhere, in all places, at all times. We imagined it as a simple attraction between objects, an invisible string pulling mass toward mass. Later, our understanding deepened. We learned to see space and time not as an empty stage, but as a unified fabric, a flexible, yielding landscape. When a massive object like a star or a planet rests within this fabric, it creates a gentle curve, a depression in the weave of space-time. Gravity, in this beautiful understanding, is simply the geometry of the universe. Objects do not pull on each other directly. Rather, they follow the natural curving paths created by the presence of mass. The Earth orbits the Sun because it is rolling along the gentle slope the Sun has pressed into the fabric of space. It is a remarkably elegant system. It is balanced, it is symmetrical. And for a long time we believed that this beautiful set of rules applied universally, with perfect consistency, to every corner of the cosmos. We believed that if you understood how gravity worked here, in our small, quiet corner of the solar system, you understood how it worked everywhere. But the universe is vast, and it is holding on to secrets that we are only just beginning to uncover. As our telescopes have grown larger, and as our instruments have become more sensitive, we have cast our gaze further out into the deep, dark ocean of space. We have mapped the positions of galaxies, measured their speeds, and traced their ancient paths across the void. And as we have done this, we have begun to notice something strange, something entirely unexpected. When we look out at the grandest scales of the cosmos, when we zoom out far beyond our own galaxy, beyond our local group of galaxies, and look at the vast, sweeping currents of the universe, the rules seem to change. The math begins to fray. The predictions do not quite match the reality we observe. We have found that gravity is behaving differently in this area. When we say this area, we are not talking about a small, localized region. We are not talking about a strange planet or a single, peculiar star system. We are talking about vast, sweeping stretches of the cosmos. We are talking about regions of space so unimaginably immense that light itself takes millions, even billions, of years to cross them. In these colossal domains, the elegant, predictable force of gravity seems to be acting in ways that defy our standard expectations. It is as if we have spent our whole lives studying the currents of a small, quiet pond, only to suddenly discover the powerful swirling undertows of the deep ocean. The water is the same, but the forces at play are operating on a scale, and in a manner that challenges everything we thought we knew. Imagine, for a moment, the fabric of space-time once again. In our local neighborhood, the curves are gentle, well-understood dips created by our sun and the nearby stars. But far out in the deep universe, there are regions where this fabric appears to be drawn, pulled, and stretched by forces we cannot see and cannot fully explain. Galaxies, those magnificent islands of billions of stars, are not drifting aimlessly. They are flowing. They are moving in vast rivers of light and mass, drawn together by an immense, unseen gravitational pull. Yet, when we count up all the visible matter in these regions, all the stars, all the glowing gas, all the dust, there is simply not enough of it to generate the kind of gravity required to move galaxies in this way. The math does not add up. There is a missing piece to the puzzle. In these vast areas, gravity is far stronger, far more influential, than it has any right to be based on the matter we can observe. It is a quiet, profound mystery that whispers to us from the dark spaces between the stars. It tells us that our understanding of the universe is still incomplete, that the grand architect of gravity holds secrets we have yet to fathom. As we drift further into this exploration, we must let go of the comforting certainty of our local, well-behaved gravity. We must prepare to venture into the deep waters of the cosmos, where the invisible forces of nature are shaped by entities and phenomena that elude our eyes. We're going to journey into the regions where gravity behaves differently, exploring the unseen mass, the hidden currents, and the colossal structures that pull at the very fabric of our reality. To understand how gravity is behaving differently, we must first understand the concept of cosmic flow. When you look at a river, you do not just see isolated drops of water, you see a collective movement. The water follows the contours of the landscape, flowing over smooth stones, gathering in deep pools, and rushing down steep inclines, all guided by the unseen hand of gravity. The universe, it turns out, has its own topography and its own rivers. These rivers are not made of water, of course. They are made of galaxies. For decades, astronomers believed that the expansion of the universe was a relatively uniform process. Following the initial outward burst of the cosmos, it was thought that everything was simply drifting apart from everything else in a steady, predictable manner. If you were to blow up a balloon with small dots drawn on it, every dot would move away from every other dot as the balloon expanded. This was the accepted picture of our expanding universe. However, as we developed the tools to map the universe in 3 dimensions, a new and startling picture began to emerge. The expansion of the universe is not entirely uniform. While space itself is expanding, pushing galaxies apart, gravity is fighting a local, quiet rebellion. Gravity acts as a counterforce to the expansion. Where matter is dense, gravity acts like a localized anchor, pulling things together even as the fabric of space stretches. And what we discovered is that galaxies are not just moving outward, they are also moving sideways. They are drifting through space, falling toward regions of immense density. We, too, are falling. Our Milky Way galaxy, along with our neighboring galaxy Andromeda and dozens of smaller satellite galaxies, make up what is known as the local group. This entire local group is currently moving through space at an astonishing speed of roughly 600 kilometers per second. That is over 3 million miles per hour. We are hurtling through the cosmos. But toward what? For a long time, the destination of this grand cosmic journey was shrouded in mystery. The reason for this mystery was simply our own location. Our solar system sits embedded within the disk of the Milky Way. When we try to look out into the wider universe in certain directions, our view is blocked by the thick bands of interstellar dust, gas, and stars that make up our own galaxy. Astronomers call this region the zone of avoidance. It is a cosmic blind spot, a dense, glowing fog that obscures roughly 20% of the deep sky. Imagine trying to look at the landscape surrounding your house, but a thick, impenetrable wall of mist surrounds your porch. You know there is something out there, but you cannot see it. For a long time, the driving force behind our galaxy's incredible speed lay hidden perfectly behind this zone of avoidance. We knew we were being pulled, but we could not see the hand that was pulling us. It was a gravitational anomaly. Gravity was pulling us with immense force, but the source of this gravity was invisible. Eventually, as we developed instruments capable of peering through the dust using infrared and radio wavelengths, the fog began to clear. And what emerged from the shadows was staggering. Hidden behind the dusty veil of the Milky Way was an unimaginably massive concentration of matter. It was not a single giant star, nor was it a supermassive black hole. It was a dense, sprawling congregation of thousands upon thousands of galaxies, all bound together in a massive gravitational embrace. This region was named, quite fittingly, the Great Attractor. The Great Attractor is a gravitational focal point, an area of such extreme mass that it acts as the bottom of a cosmic valley. Just as water flows down the sides of a mountain to gather in a basin, hundreds of thousands of galaxies, including our own, are flowing like a slow, majestic river down the gravitational slopes toward the Great Attractor. We are part of a massive, overarching structure of galaxies, a supercluster known as Laniakea, which translates to immense heaven in the Hawaiian language. The Great Attractor lies at the very heart of Laniakea, serving as the gravitational anchor for our entire region of the universe. Yet, even as the mystery of the Great Attractor was unveiled, the story was not complete. Gravity, it seemed, was still behaving differently than our models predicted. Even when astronomers calculated the combined mass of all the thousands of galaxies within the Great Attractor, all the visible light, all the X-ray emitting gas, and all the dark matter they could infer, it was still not quite enough. The mass of the Great Attractor was immense, yes, but it was not quite immense enough to fully explain the incredible speed at which our local group is hurtling through space. The math was closer, but there was still a discrepancy. There was still an anomaly. If the Great Attractor was not solely responsible for our velocity, what else was influencing our journey? The answer required a shift in perspective. For centuries, we have thought of gravity exclusively as a pulling force. We think of mass attracting mass. But in the vast, complex fluid dynamics of the cosmos, the absence of mass can be just as influential as the presence of it. If you have a region of space that is incredibly dense, packed with galaxies, it exerts a strong gravitational pull. But what happens if you have a region of space that is virtually empty? The universe is not an even distribution of matter, it is a web. It is built of dense filaments of galaxies, glowing nodes where these filaments intersect, and vast, dark, empty spaces in between. These empty spaces are known as cosmic voids. They are the deserts of the universe, regions spanning hundreds of millions of light years across where almost nothing exists. No stars, no galaxies, no gentle glow of dust. Just pure, silent emptiness. While a dense cluster of galaxies pulls matter toward it, a cosmic void does the exact opposite. Because it lacks mass, it lacks gravitational pull. And in a universe where everything is pulling on everything else, an area that does not pull essentially acts as a push. Imagine a tug of war. If the team on the left suddenly lets go of the rope, the team on the right will fall backward. The team on the left didn't actively push them, they simply ceased to pull. In the cosmos, matter flows away from the empty voids and toward the dense clusters. And recently, scientists discovered a massive void sitting right behind us. If the Great Attractor is pulling us forward, this immense empty region, dubbed the dipole repeller, is effectively pushing us from behind. The dipole repeller is a region of profound nothingness. It is an expanse of space so devoid of matter that it creates a negative gravitational influence on its surroundings. We are caught in the middle of a grand cosmic flow, being drawn toward the mass of the Great Attractor and simultaneously fleeing from the emptiness of the dipole repeller. This interplay between the pull of the dense and the push of the void is a beautiful, subtle manifestation of gravity behaving differently on a macroscopic scale. It shows us that to understand the motion of the universe, we cannot just look at the bright, shining objects. we must also listen to the silence of the empty spaces. We must recognize that the architecture of space-time is shaped just as much by what is missing as by what is present. The great attractor and the dipole repeller guide our slow, majestic drift through the cosmos. But even with these massive structures accounted for, the deep underlying question of how gravity operates in these vast domains remains. We have identified the currents, but the true nature of the water itself is still a profound mystery. As we continue to drift, we must delve into the unseen substance that binds these galaxies together, a ghost in the cosmic machine that silently alters the rules of attraction. As we leave behind the grand, sweeping currents of the great attractor and the quiet emptiness of the dipole repeller, we must zoom our perspective back in. We must look not at the flow of millions of galaxies, but at the behavior of a single one. Because to truly understand how gravity is behaving differently, we must look at the way galaxies spin in the lonely dark of space. Imagine, if you will, a classic spiral galaxy. It is a beautiful, familiar shape, a bright, dense core of ancient glowing stars surrounded by a flat disk of sweeping, graceful arms. These arms are laced with glowing pink nebulae, the cold, dark dust of creation, and billions of individual stars, all gently orbiting the galactic center. In our everyday experience, we understand how spinning objects behave. Think of a merry-go-round in a quiet park. If you stand near the center, you turn relatively slowly. But if you stand on the very outer edge, you must move much faster to keep up with the rotation. However, gravity dictates a different set of rules for objects in orbit. Within our own solar system, the planets closest to the Sun, like Mercury and Venus, feel a tremendous gravitational pull. To avoid falling into the Sun, they must travel at incredible speeds along their orbital paths. Mercury whips around the Sun in a mere 88 days. But as you move further out, the gravitational grip of the Sun grows weaker. The outer planets, like Neptune and Uranus, drift along their paths at a much more leisurely pace. Neptune takes over 160 Earth years to complete a single journey around the Sun. The rule is simple and mathematically precise. The further you are from the central mass, the slower you orbit. This is a fundamental consequence of gravity, as laid out by Isaac Newton and later refined by Albert Einstein. It is a rule that we expect to hold true everywhere. For a long time, astronomers assumed that galaxies would obey this exact same rule. A galaxy, after all, is just a larger system of orbiting bodies, the vast majority of a galaxy's visible mass. The blinding concentration of stars and gas is packed tightly into its central bulge. Therefore, it stood to reason that the stars near this dense, heavy core would orbit very quickly, while the lonely stars scattered on the very outermost edges of the spiral arms would orbit much more slowly. In the middle of the 20th century, astronomers began to carefully measure the speeds of these outer stars. They used instruments that could detect the subtle shifts in the light emitted by the rotating gas and stars, a gentle reddening or bluing of the light that revealed how fast the material was moving toward or away from us. They expected to see the speeds drop off smoothly as they looked further and further from the galactic center. They expected to see the familiar, comforting rules of gravity at play. But that is not what they found. When the measurements were finally plotted, the result was a profound and quiet shock to the scientific community. The stars on the outer edges of the galaxies were not slowing down. Instead, they were moving at roughly the same speed as the stars, much closer to the center. The rotation curve did not drop, it remained flat. To understand how strange this is, imagine watching a flock of birds circling a central point. The birds on the outer edge of the flock are flying at the exact same furious speed as the birds in the middle, yet they are traveling a much wider circle. According to everything we know about gravity, this should be impossible. A star on the outer edge of a galaxy, moving at such immense speeds, should simply fly off into the void of intergalactic space. The visible mass of the galaxy, the glowing core and the scattered stars of the disk, does not possess nearly enough gravity to hold on to these fast-moving outer stars. The centrifugal force of their rotation should tear the galaxy apart, scattering its beautiful spiral arms into the empty dark. Yet, the galaxies remain intact. They spin beautifully, serenely, holding their shapes across billions of years. This presents a quiet, unavoidable paradox. Either our fundamental understanding of gravity is fundamentally flawed on these large scales, or there is something else there. There must be a vast invisible anchor holding these galaxies together. When scientists calculated exactly how much mass would be required to keep these fast-moving outer stars in their orbits, the answer was staggering. The visible matter, every shining star, every glowing cloud of gas, every speck of obscuring dust, accounted for only a tiny fraction of the necessary gravity. To keep the galaxy from tearing itself apart, there had to be roughly 5 to 6 times more mass hidden in the dark than was shining in the light. This unseen substance became known as dark matter. The name is perhaps a bit misleading, for it is not simply dark in the way that a thundercloud is dark, or in the way that a soot-covered rock is dark. Those things are dark because they absorb light or block it. Dark matter is entirely different. It is perfectly transparent. It does not emit light, it does not reflect light, and it does not absorb light. It does not interact with the electromagnetic spectrum in any way that our instruments can detect. If you were to hold a lump of dark matter in your hand, you would not be able to see it. You would not be able to feel it. It would pass right through your skin, through the floor beneath you, and through the earth itself, slipping between the atoms of ordinary matter like a ghost through a wall. The only way we know it exists, the only way it speaks to the universe, is through the gentle, persistent pull of its gravity. We now understand that the beautiful, glowing spiral galaxies we see in our telescopes are merely the bright, shining cores of much larger, invisible structures. Every galaxy is encased in a massive, spherical halo of dark matter. This halo extends far beyond the visible edges of the spiral arms, reaching out into the cold void. It is the deep, unseen foundation upon which the luminous galaxy is built. It is a humbling realization. The matter that makes up you and me, the Earth, the Sun, and every star we have ever seen in the night sky is not the primary ingredient of the universe. We are a minority. We are the glowing foam resting on the surface of a deep, dark, and invisible ocean. Gravity is behaving differently here because it is responding to a massive, silent presence that we cannot see. The universe is heavier, denser, and far more mysterious than it appears to the naked eye. And as we look deeper into the cosmos, this invisible scaffolding only becomes more profound. To truly grasp the immense scale of this invisible foundation, we must journey beyond the borders of a single galaxy. We must travel out into the vast open plains of the cosmos, where gravity gathers galaxies together into the largest, most massive structures in the universe, galaxy clusters. A galaxy cluster is exactly what it sounds like, a magnificent congregation of hundreds, sometimes thousands, of individual galaxies, all bound together by a shared gravitational embrace. They are cities of light in the dark expanse of space. Between these galaxies, the space is not entirely empty. It is filled with a thin, incredibly hot gas that glows softly in X-ray light, a remnant of the fierce cosmic forces that forged the cluster. If dark matter forms a halo around a single galaxy, what does it do in a cluster of thousands? Nearly a century ago, long before the rotation curves of individual galaxies were measured with precision, an eccentric and brilliant astronomer named Fritz Zwicky was studying a massive group of galaxies known as the Coma Cluster. He carefully observed the individual galaxies within the cluster, measuring how fast they were moving as they swarmed around one another like bees in a hive. What he found mirrored the mystery of the spinning galaxies, but on a scale that was unimaginably larger. The galaxies within the Coma Cluster were moving far too fast. They were zipping through the cluster at velocities so high that the gravitational pull of the visible galaxies, and even the massive clouds of hot gas between them, should not have been able to keep them contained. The cluster should have evaporated, its member galaxies flying off into the void like untethered balloons. But, just like the spinning spiral galaxies, the Coma Cluster remained bound. It held together, a stable, enduring structure. Zwicky concluded that there had to be an enormous amount of unseen, dunkel materie, of dark matter holding the cluster together. For decades, his observations were considered a curious anomaly, a mathematical quirk that would eventually be explained away. But it was not a quirk. It was the first quiet whisper of the true nature of the universe. Today, we have entirely new ways of seeing this invisible mass. We do not just rely on the speed of moving galaxies, we can actually see the gravity of dark matter bending the very fabric of reality. Albert Einstein taught us that mass bends space, and that light traveling through space must follow those bends. If you place a very massive object between Earth and a distant light source, the gravity of that massive object will curve the space around it. When the light from the distant source passes by, it follows that curve, bending around the massive object before traveling on to reach our telescopes. This effect acts like a colossal, cosmic magnifying glass. It is called gravitational lensing. When we look at massive galaxy clusters, we often see something exceptionally beautiful and strange. Scattered behind the cluster, far off in the deeper ancient universe, are other, more distant galaxies. As the light from these background galaxies travels toward us, it passes through the foreground cluster. Because the foreground cluster is so massive, its gravity severely warps the space around it. The light from the background galaxy is bent, stretched, and distorted. When it reaches our eyes, we do not see a perfect, sharp image of the background galaxy. Instead, we see strange, elongated arcs of light smeared out along the edges of the cluster. Sometimes, the light is bent so perfectly that we see multiple mirrored images of the exact same background galaxy floating like phantoms around the cluster's core. By carefully measuring the exact shape and curvature of these distorted arcs of light, astronomers can work backward. They can calculate exactly how much mass is required to bend the light in that specific way. They can map the invisible topography of the cluster. When they do this, the results are conclusive and awe-inspiring. The amount of mass required to create the gravitational lensing we observe is vastly greater than the mass of all the visible galaxies and the hot gas combined. The lensing reveals that the entire galaxy cluster is sitting at the bottom of a colossal, invisible basin of dark matter. The dark matter is not just surrounding the individual galaxies, it fills the spaces between them, creating a massive, enveloping cloud that holds the entire city of light together. Perhaps the most striking and beautiful proof of this unseen universe comes from a cosmic event known as the Bullet Cluster. The Bullet Cluster is not a single, peaceful group of galaxies. It is the site of a titanic collision. Millions of years ago, two separate, massive galaxy clusters crashed into one another at unimaginable speeds. When clusters collide, it is a slow, majestic, and violent process. The individual galaxies within the clusters are spaced so far apart that they mostly slip past one another like ghosts. But the vast clouds of hot gas that fill the spaces between the galaxies do not. As the two clusters collided, these immense clouds of gas slammed into each other, creating a massive, glowing shockwave shaped like a bullet that slowed down and pooled in the center of the collision. But what happened to the dark matter? Dark matter, remember, does not interact with light, and it does not interact with normal matter. It seems, in fact, that it barely interacts with itself. When astronomers pointed their telescopes at the Bullet Cluster, they looked at it in two different ways. First, they looked at the X-rays, mapping the location of the ordinary visible matter, the hot gas that had crashed and stopped in the middle. Then, they looked at the gravitational lensing, tracing the distortions of background light to map the location of the total mass. What they saw was a complete separation. The vast majority of the mass in the collision was not located where the hot gas had pooled. Instead, the gravity was centered on two invisible, ghostly blobs that had sailed right through the collision without slowing down. The dark matter from the two clusters had passed completely through one another, undisturbed and unhindered, carrying the individual galaxies along with them. It is as if two heavy, invisible bowling balls were thrown at each other, each carrying a cloud of luminous dust. When they met in the middle, the dust crashed and billowed, but the invisible bowling balls kept right on rolling. The The bullet cluster is a quiet, profound testament to the reality of the unseen universe. It shows us, with beautiful clarity, that gravity is behaving differently because the bulk of the universe is made of something we simply cannot perceive with our eyes. The light we see, the stars we name, the galaxies we map, these are merely the illuminated dust motes floating in a vast, dark room. Gravity is the architect, but dark matter is the building material. It forms the invisible framework, the deep, heavy valleys of space-time into which all the normal matter of the universe flows, gathers, and eventually ignites into stars. As we drift deeper into this understanding, we must accept that the universe is largely a shadow realm. The forces that guide the galaxies, the invisible hands that shape the cosmic web, operate in a darkness that is not empty, but profoundly, heavily full. We have traveled from the gentle, familiar pull of our own Earth to the roaring, unseen currents of the Great Attractor. We have watched galaxies spin, held together by the invisible, heavy hand of dark matter, and we have witnessed the titanic collisions of galaxy clusters where this ghostly substance passes freely through the fire. We have seen that the universe is largely built of something we cannot see, a hidden scaffolding that dictates the flow and structure of the cosmos. But as we cast our gaze out to the absolute limits of our vision, to the deepest, most ancient edges of the observable universe, we encounter an anomaly that dwarfs all others. In the vast, open ocean of deep space, far removed from the dense, glittering cities of galaxy clusters, gravity is not just behaving differently, it appears to be losing its grip entirely. To understand this ultimate mystery, we must look at the empty spaces. We must look at the cosmic voids, those colossal, silent deserts where almost no matter exists. For a very long time, cosmologists held a simple, logical belief about the future of the universe. We knew the universe was expanding, a remnant of the initial, magnificent outward burst of creation. But we also knew that the universe was filled with mass stars, galaxies, black holes, and the vast, unseen oceans of dark matter. Because gravity is an attractive force, it was assumed that the collective gravity of all this mass must be acting as a colossal brake. Imagine throwing a stone high into the air. It leaves your hand with a burst of speed, but almost immediately, the gravity of the Earth begins to pull it back. The stone slows down, eventually reaches a peak, and then falls. Scientists believed the universe was acting much like that stone. The expansion was pushing everything apart, but the combined gravity of all the matter in the cosmos was tirelessly pulling it all back together. The great debate of the 20th century was simply a matter of measuring the brakes. Was there enough mass in the universe to eventually bring the expansion to a halt, causing the cosmos to slowly collapse back in on itself? Or was the initial outward push so strong that the universe would expand forever, albeit at a slower and slower pace as the eons ticked by? In either scenario, one thing was absolutely certain: the expansion of the universe had to be slowing down. Gravity demanded it. The rules were clear. In the late 1990s, two independent teams of astronomers set out to measure this deceleration. They wanted to know exactly how fast the universe was slowing down, and to do this, they needed to look at objects that were incredibly far away. They needed cosmic lighthouses, beacons of known brightness that could be seen across billions of light-years of space. They found their lighthouses in a very specific, beautiful type of stellar death known as a Type Ia supernova. A Type Ia supernova occurs in a binary star system where a small, incredibly dense dying star called a white dwarf orbits a larger companion star. The white dwarf, possessing immense gravity, slowly steals gas from its neighbor, pulling the material down onto its own surface. It gorges itself, growing heavier and heavier until it reaches a very specific, absolute mass limit. When it crosses this precise threshold, the white dwarf can no longer support its own weight. In a single, blinding instant, it ignites in a thermonuclear explosion of unimaginable power. Because every Type Ia supernova detonates at the exact same mass limit, they all explode with the exact same innate brightness. They are standard candles. If you see a Type Ia supernova in a distant galaxy and it appears very dim, you know it is only dim because it is very far away. By carefully measuring how faint these explosions appear, astronomers can calculate exactly how far the light has traveled. And by analyzing how much the light from the explosion has been stretched, a phenomenon called redshift, they can measure how much the universe has expanded since the star exploded. The astronomers pointed their telescopes into the deepest dark, hunting for these dying stars. They gathered their data, expecting to find the subtle signature of a universe gently applying the brakes. They expected to see that the expansion was slowing down under the heavy collective pull of all the dark matter and visible galaxies. Instead, the universe offered them a profound, paradigm-shifting silence. The supernovas they found were too dim. They were much fainter than the models predicted. The only logical explanation for this faintness was that the supernovas were farther away than they should have been. And the only way they could be that far away was if the expansion of the universe had not been slowing down over the past few billion years. It had been speeding up. This discovery sent a quiet shockwave through the scientific community. It was a realization as profound as discovering that a stone thrown into the air does not slow down and fall back to Earth, but instead accelerates, rocketing upward faster and faster into the sky. Gravity, the great binder, the force that we trusted to hold the cosmos together, was being overpowered. On the grandest scales of the universe, gravity is behaving differently because it is no longer the dominant force. There is something else in the dark. There is a presence, an energy, woven into the very fabric of space itself. We call it dark energy. If dark matter is the unseen scaffolding that pulls galaxies together, dark energy is the invisible breath that is blowing the universe apart. It does not exist in clumps like matter. It does not gather in galaxies or form heavy dark halos. Instead, it seems to be a property of space itself. It is everywhere. It is in the room with you now. It is in the space between the Earth and the Moon, and it fills the vast, empty voids between the galaxy clusters. As the universe expands, more space is created. And because dark energy is a property of space, as more space comes into existence, the total amount of dark energy increases. It is a relentless, compounding force. For the first few billion years of the universe's life, the universe was smaller and matter was packed more closely together. In that early epoch, the gravitational pull of dark matter was strong enough to dominate, drawing the hot gas together to forge the first stars and galaxies. It was a time of gathering, a time of building. But as the universe continued to expand, the matter became spread out. The galaxies drifted further apart, and the gravitational pull between them grew weaker. Meanwhile, the dark energy, rising from the ever-increasing volume of empty space, grew stronger and stronger. Roughly 5 billion years ago, a quiet transition occurred. The outward push of dark energy finally overtook the inward pull of gravity. The expansion of the universe stopped slowing down and began to accelerate. This is the ultimate mind-bending reality of the cosmos. When we look at the deep empty regions, the cosmic voids, we are looking at the engines of our separation. In these areas, gravity is behaving differently because the empty space itself is pushing outward, stretching the fabric of reality, driving the galaxy clusters apart at ever-increasing speeds. We find ourselves then suspended in a delicate cosmic tension. We are passengers on a tiny rocky world, drifting through a universe that is locked in a slow, majestic tug-of-war between two invisible, incomprehensible forces. On one side is the dark matter, the heavy, silent architect. It is the deep gravity that holds our Milky Way together, ensuring that our sun remains in its orbit, keeping the stars from flying off into the cold dark. It is the force that weaves the galaxies into the magnificent glowing strands of the cosmic web, creating islands of light and structure where life can briefly, beautifully bloom. On the other side is the dark energy, the relentless, quiet expander. It is the phantom pressure arising from the void, stretching the canvas of the universe, ensuring that the vast distances between the galaxy clusters will only ever grow wider, darker, and more profoundly silent. When we say that gravity is behaving differently in this area, we must realize that this area is the entirety of our known reality. The rules we learned on the surface of our small planet, the simple laws of falling apples and orbiting moons, are merely localized habits. They are the gentle, predictable behaviors of a force that, on a grander scale, operates in a realm of shadow and profound emptiness. The universe is not just heavier than we thought, it is also more repulsive. It is pulling itself together locally, while tearing itself apart globally. There is a strange, peaceful poetry to this realization. It teaches us that our intuition, born from our everyday experiences on a solid, sunlit world, is not perfectly equipped to understand the deep, ancient mechanics of the cosmos. The universe does not owe us simplicity. It does not owe us an easy, comforting explanation. Instead, it offers us majesty. It offers us mysteries so vast that they force us to expand our minds, to rethink our place in the grand design, and to marvel at the intricate, invisible architecture that surrounds us. As we look toward the future, the accelerated expansion driven by dark energy paints a picture of a slow, gentle fading. The universe is not destined to end in a fiery collapse, crushed back into a single point of infinite density, nor will it tear apart violently in an instant. Instead, the expansion will continue to accelerate quietly and tirelessly. Over billions and trillions of years, the vast spaces between the galaxy clusters will grow so wide that light from one cluster will no longer be able to reach another. The cosmic web will slowly stretch and fade. The galaxies will become isolated islands, drifting alone in an ever-expanding, ever-cooling sea of total darkness. Eventually, even the stars within those isolated galaxies will burn through their fuel. They will flicker, cool and dim. The universe will settle into a deep, eternal slumber, a state of perfect, infinite peace. It is a quiet, melancholic destiny, but it is one completely devoid of chaos. It is the final, ultimate stillness. But that time is unimaginably far away. For now, we are here. We exist in the era of light, in the era of structure, perfectly balanced between the pull of the dark matter and the push of the dark energy. Imagine, once again, the night sky. If you open your eyes or simply bring your awareness back to the present moment, you can picture those scattered silver stars. The silence of the night is still there. The comforting constellations remain. But perhaps now, when you look up, the stillness no longer looks like a frozen painting. Perhaps you can feel, just for a fleeting moment, the immense, invisible currents moving in the dark. You can imagine the Milky Way, wrapped in its heavy halo of dark matter, hurtling through the void toward the Great Attractor, pulled by a congregation of mass so large it defies human comprehension. You can feel the quiet, empty breath of the dipole repeller pushing us gently from behind. You can picture the ancient light of distant supernovas, stretched and weary, whispering the secret of the expanding, accelerating space between the galaxies. You are a part of this. The atoms in your body, the iron in your blood, the calcium in your bones, they were all forged in the hearts of stars that were gathered together by the unseen gravity of dark matter. We are the children of this majestic tension. We are the rare, illuminated matter, given a brief moment of consciousness to look out into the dark and wonder. The universe is vast, and it is holding on to secrets we may never fully uncover. Gravity is behaving differently in this area, and in that difference lies the profound, unfolding story of our existence. There is no need to fear the dark or to be overwhelmed by the scale of the cosmos. The invisible forces that shape reality are ancient, slow, and mathematically serene. They have guided the galaxies for billions of years, and they will continue their quiet work long after we are gone. So let the vastness comfort you. Let the gentle mysteries of the deep sky wash over you. The universe is expanding, the galaxies are flowing, and gravity is painting a masterpiece on a canvas we cannot fully see. Rest in the knowledge that you are a part of this beautiful, intricate design. The night is deep, the cosmos is holding you perfectly in place, and all is exactly as it should be. As we have drifted through the vast, expanding voids and marveled at the heavy, invisible halos of dark matter, we have seen how gravity shapes the universe on its grandest scales. We have watched it gently guide the rivers of galaxies and quietly lose its grip in the deep, empty deserts of space. But to fully understand the profound strangeness of this force, we must also look at where it goes to its absolute, unimaginable extreme. We must travel from the widest, most scattered expanses of the cosmos into the tightest, darkest, and most profound points of existence. We must journey to the places where the fabric of space-time is not just stretched or gently curved, but where it is pulled so deeply that it tears. In these precise, silent locations, gravity is behaving differently because the rules of our reality simply cease to function. We are talking about black holes. For a long time, black holes were nothing more than a mathematical curiosity. They were a bizarre consequence hidden within Albert Einstein's beautiful equations, a theoretical concept that seemed too strange, too extreme, to actually exist in the physical universe. The math suggested that if you could somehow compress a massive amount of matter into an incredibly small space, the gravitational pull would become so intense that nothing, not even light, could escape its grasp. It was a daunting thought, a place where the universe simply closes its doors. But as our telescopes peered deeper into the hearts of galaxies, we realized that these mathematical ghosts were real. In fact, they are everywhere. When a massively heavy star reaches the very end of its long life, having burned through all its nuclear fuel, it can no longer support its own immense weight. The outward push of its glowing fires ceases, and the inward pull of its own gravity takes over completely. The star collapses. It falls in on itself with terrifying, silent speed. The matter is crushed, the atoms are broken, and the core of the star shrinks down until it becomes a point of infinite density, a single, unfathomable speck known as a singularity. Around this singularity is a boundary, a perfectly spherical threshold in space called the event horizon. This is the point of no return. Once anything. A wandering comet, a cloud of interstellar dust, or a beam of starlight crosses the event horizon, it is caught. The gravity here is so overwhelmingly strong that the escape velocity exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing can ever leave. But it is not just light that is trapped. It is here, at the edge of the black hole, that we see gravity's most profound and disorienting effect. Gravity does not just bend space, it bends time. Imagine you are in a small spacecraft, hovering safely at a great distance from a black hole, watching a brave robotic probe slowly descend toward the dark, silent sphere of the event horizon. As the probe gets closer and closer to the boundary, the gravity it experiences grows exponentially stronger. Because gravity warps the flow of time, an observer in the strong gravitational field will experience time moving more slowly than an observer in a weaker gravitational field. From your safe vantage point far away, you would see something incredibly strange happen to the probe. As it approaches the black hole, its descent would appear to slow down. The flashing light on its hull would blink less and less frequently. As it reaches the very edge of the event horizon, it would seem to stop completely. To your eyes, the probe would never actually cross the threshold. It would simply freeze there, its image slowly fading, becoming dimmer and redder as the light struggling to reach you loses its energy to the immense gravitational pull. Time, for the probe, is passing differently than it is for you. In this area, gravity is so intense that it has effectively brought the forward march of time to a standstill for anyone watching from the outside. It is a beautiful, peaceful kind of illusion. A black hole does not just consume matter, it captures moments. It freezes the universe at its absolute edge, creating a gallery of perfectly still, fading phantoms. Yet, for the probe itself, there is no freezing. If it possessed consciousness, it would feel itself falling smoothly, seamlessly across the boundary and into the profound dark, entirely unaware that the rest of the universe was watching it freeze in time. It would enter a realm where all paths lead inward, where space itself is falling toward the center faster than light can travel. We cannot see inside a black hole. The event horizon is a veil of absolute secrecy. We do not know what happens to the matter that falls within, or how the laws of physics operate at the singularity. Our current understanding of the universe, the delicate dance between the heavy and the light, the push and the pull, breaks down completely in this invisible, infinitely deep well. Black holes remind us, gently but firmly, that the universe is not obligated to be completely understood. There are rooms within the grand mansion of the cosmos where the doors are locked and the key has been thrown away. In these regions, gravity is the ultimate keeper of secrets, guarding the deepest mysteries of space, time, and matter with an unbreakable, silent embrace. For centuries, our relationship with the universe has been entirely visual. We have been a quiet audience sitting in a darkened theater, watching the grand, luminous play of the cosmos unfold. We have gathered the light of distant stars, captured the X-ray glow of ancient collisions, and mapped the twisted arcs of gravitational lenses. Everything we knew about the universe we learned by looking. But gravity is not a source of light. It is the unseen canvas upon which the light travels. And recently, we learned that this canvas does not just bend and curve, it ripples. Imagine standing on the shore of a perfectly calm, still lake in the early hours of the morning. If you toss a heavy stone into the center of the water, it breaks the surface, and a series of concentric waves travels outward, gently lapping against the shore moments later. Space-time behaves in much the same way. When something incredibly massive moves, it sends invisible ripples traveling outward through the fabric of the universe. We call these ripples gravitational waves. Albert Einstein predicted their existence over a century ago. He understood that if space and time were a connected, flexible medium, then truly violent cosmic events must cause that medium to vibrate. But he also believed that these waves would be so incredibly subtle, so infinitesimally small by the time they reached Earth, that humanity would never possess the technology sensitive enough to detect them. For once, Einstein underestimated our quiet, persistent curiosity. Billions of years ago, in a galaxy far removed from our own, two black holes found themselves caught in a fatal, spiraling dance. They were incredibly massive, each one dozens of times heavier than our own sun, and they were orbiting one another at a frantic, unimaginable speed. As they circled closer and closer, their immense gravity churned the fabric of space-time around them. They were like two heavy stones swirling in our calm lake, sending out massive invisible waves of gravitational energy into the dark. Eventually, in a fraction of a second, they collided. They merged into a single, heavier black hole. The sheer power of that silent impact was greater than the combined light of every single star in the observable universe. But it did not emit a single spark of light. All of that immense, staggering energy was poured directly into the fabric of space itself, creating a final, powerful crescendo of ripples that shot outward at the speed of light. For over 1 billion years, those ripples traveled through the silent void. They passed through ancient galaxy clusters, they washed over vast empty regions of dark energy, and they swept through the dusty halos of dark matter. As they traveled, they expanded and weakened, becoming quieter and softer. Finally, they reached our small blue planet. As the wave passed through the Earth, it did something extraordinary. It actually stretched and squeezed the space we occupy. For a fraction of a heartbeat, the entire planet, every building, every tree, and every person was stretched slightly taller and then squeezed slightly wider. The change was incredibly small, a fraction of the width of a single proton. It was a movement so delicate that it was entirely unfelt by human senses. But we had built massive, incredibly sensitive machines, great L-shaped vacuum tubes stretching for miles, designed specifically to feel this tiny, fleeting breath of the cosmos. When the wave passed through our detectors, the lasers within them shifted just enough to register the movement. We caught the signal. We recorded the ripple. For the first time in human history, we did not just look at the universe, we listened to it. When scientists converted the signal of that gravitational wave into an audio frequency, it produced a short, deep sound. A quiet chirp. It was the sound of space itself ringing like a bell, struck by the silent collision of two invisible giants a billion light-years away. This brings us to a profound and beautiful realization about how gravity is behaving in our universe. It is not just a static set of rules. It is not just the heavy foundation or the inescapable well. It is a dynamic, living medium. The universe is vibrating with the echoes of ancient, unseen movements. Every time a star explodes, every time two dense objects merge in the dark, they send a gentle tremor through the very space that surrounds us. We are swimming in a cosmic sea that is constantly, quietly shimmering with gravitational waves. As you lie here, safe and still, you are anchored to the earth by the gentle, familiar pull of gravity. It is the exact same force that holds the black holes in their silent dance, the same force that binds the heavy, dark halos, and the same force that carries the ripples of the distant cosmos right through your room. Gravity is the unbroken thread that connects the smallest grain of sand on our planet to the farthest, darkest edges of the observable universe. It behaves differently depending on where you look, taking on masks of incredible power, gentle persuasion, and baffling mystery. But it is always there. There is still so much we do not know. We do not fully understand the dark matter. We are baffled by the dark energy, and we cannot peer beyond the veil of the event horizon. But that is the beauty of our existence. We are a part of a universe that is endlessly deep, a cosmos that continues to reveal itself in soft, surprising whispers. Allow yourself to feel the gentle pull holding you right now. It is a safe, steady embrace. You are exactly where you are meant to be, resting in a quiet corner of a vast, vibrating, and exquisitely mysterious universe. As we listen to the quiet ringing of the cosmos, the gentle fading echoes of gravitational waves washing over our world, we must confront a startling possibility. For decades, we have built our understanding of the universe on a single massive assumption, that the unseen, heavy presence of dark matter is the only way to explain why galaxies spin so fast and why clusters hold together. We have filled the dark, empty spaces of our models with a ghostly substance simply to make the math work, simply to preserve the rules of gravity as we have always known them. But there is a small, quiet rebellion in the world of physics, a subtle, persistent question that whispers from the edges of our understanding. What if the dark matter is not there at all? What if, in these vast, lonely regions of space, gravity is not being pulled by invisible ghosts, but is instead fundamentally changing its own nature? Imagine a gentle, fading light. As you walk away from a lantern in the dark, its light grows dimmer and dimmer in a predictable, smooth way. This is how we have always believed gravity works. The further you move away from a massive object, the weaker its gravitational pull becomes, dropping off at a precise, mathematically elegant rate. But some scientists have proposed a radical, profound alternative. They suggest that when the acceleration of gravity drops to an incredibly low level, the kind of barely there, whisper-thin gravity experienced by a lonely star drifting at the very outermost edge of a galaxy, the rules suddenly shift. In this profound emptiness, where the pull of the galactic core is weaker than a breath, gravity refuses to drop off any further. It stops fading. It levels out, maintaining a stronger grip than our classical laws would ever predict. This idea is a modification of everything we know. It suggests that there is a threshold, a quiet boundary line in the deep cosmos. Once you cross it, once gravity becomes weak enough, it changes its behavior entirely. If this is true, then the fast-moving stars at the edges of the galaxies are not being held in place by massive halos of invisible matter. They are being held because, in that specific area, gravity simply does not let go. It is a beautiful, unsettling thought. It asks us to abandon the comforting universality of our physical laws. It tells us that the universe is not just strange in its ingredients, but deeply strange in its fundamental mechanics. The rules that govern the heavy, bustling centers of star systems are not the same rules that govern the cold, quiet fringes. To explore the true depths of how gravity can change, we must not only look out to the edges of galaxies, We must also look inward. We must zoom in past the planets, past the atoms, past the very building blocks of matter, down into a realm so infinitesimally small that the human mind can barely hold on to the concept of it. We must look at the quantum realm. We have spoken of space-time as a smooth, continuous fabric, a quiet lake, a yielding trampoline. On the scale of stars and planets, this is true. The curves are elegant, the waves are sweeping. But if you were to take a magnifying glass to this fabric and zoom in billions of times closer than a single electron, the smoothness disappears. At the absolute smallest conceivable scale of existence, a threshold known as the Planck length, reality ceases to be calm. It becomes a chaotic, roaring ocean of microscopic energy. Space and time themselves break down into a turbulent, shifting foam. In this microscopic storm, the elegant geometry of gravity is torn to shreds. Our two greatest achievements in understanding the universe, Einstein's smooth, curving gravity and the jittery, unpredictable laws of quantum mechanics, refuse to speak to one another in this area. When we try to calculate how gravity behaves in the quantum foam, the math does not just fray, it shatters. It produces infinities, impossibilities, and paradoxes. In the quantum world, gravity is behaving differently because, as far as we can tell, it simply ceases to make sense. It is the weakest force in the universe, incredibly feeble compared to electromagnetism or the strong nuclear force that binds atoms together. You overcome the gravity of the entire Earth simply by picking up a feather. Why is this grand architect of the cosmos so profoundly, unbelievably weak? The answer to that question might be the strangest and most beautiful secret of all. Some physicists believe that gravity is so weak and behaves so strangely because it does not fully belong to our universe. Imagine our universe not as the entirety of existence, but simply as a single, thin sheet of paper floating in a vast, multi-dimensional room. We live our lives, build our telescopes, and look out at the stars entirely confined to the surface of this paper. All the light we see, all the matter we touch, all the forces we measure, they are trapped on this single layer of reality. Except, perhaps, for gravity. Gravity might be the only force that is not bound to our surface. It might be a fundamental property of the larger room, the higher dimensional space that surrounds us. When a massive star curves the fabric of our universe, the gravity it creates does not just ripple along our thin sheet of paper, it leaks out. It radiates away into the higher dimensions, bleeding into spaces we cannot see and cannot reach. Because we only feel the small fraction of gravity that remains tethered to our universe, it appears to us as a whisper. It seems incredibly weak. We are only feeling the shadow of a force that is far grander, far more powerful, operating in a realm of existence that lies just outside the bounds of our perception. When we observe the fast-spinning galaxies, the holding together of clusters, and the accelerated expansion of the voids, perhaps we are not just looking at invisible dark matter or phantom dark energy. Perhaps we are witnessing the influence of other universes. Perhaps we are feeling the gravitational pull of massive, invisible worlds resting on other sheets of paper, hovering just a millimeter away from our own reality in the higher dimensions. It is a dizzying, magnificent thought. We are connected through the invisible thread of gravity to a reality far larger than the one we can see. The strange behaviors we observe, the anomalies and the mysteries are simply the gentle, brushing contact between our world and the vast, unseen architecture of the multiverse. As you let these thoughts drift through your mind, allow the scale of it all to bring you a sense of peace. You do not need to solve the equations. You do not need to build the telescopes. You only need to exist here and now in this quiet moment. The universe is infinitely complex, a tapestry woven with forces that change, leak, and behave in beautifully unexpected ways. But it is also incredibly steady. The gravity that holds you to your bed, that keeps the air in our atmosphere and the moon in its slow silver orbit, is safe. It is reliable. Whether it is leaking from a higher dimension, or changing its rules in the deep dark, or gently rippling from ancient collisions, it is the force that embraces you. It is the quiet, heavy blanket of the cosmos, wrapping around the Earth, holding everything in a delicate, perfectly balanced suspension. So let the night sky be a comfort. Let the dark spaces between the stars remind you not of emptiness, but of a profound, hidden fullness. The mysteries of the universe will continue to unfold, slowly, over thousands of lifetimes. But for tonight, the work is done. The stars will keep their watch, the galaxies will continue their slow, majestic flow, and the quiet, invisible hands of gravity will hold you safely in the dark.